In this lesson, we'll introduce the precise definition of a limit, as well as review some background information about absolute values. In example 1, I'd like to solve these absolute value equations and inequalities. Starting with this one here, there are two solutions to this equation, the absolute value of x is equal to 2. The number 0 is the center. That's the number that makes this equal 0 overall. And if you plug in positive 2 or negative 2, those are both solutions to this equation. So the absolute value is telling you the distance you are from 0, and you get two answers. Now, what if we change this, though, from an equal to a less than? Now what's the solution? Your center is still at 0, but this time your distance is less than 2. So you can go up to 2, but you can't include it, so I'll put this open circle here. And you can go down to negative 2, but you can't include that either. So your solution is really all numbers that are between negative 2 and positive 2. So I'll write it like this. So again, we're still talking about a distance, but not when it's equal, when it's less than 2. Continuing with this idea in the last one, when is the absolute value of x minus 1 less than 2? We still have a less than 2, so we're talking about a distance of 2, but by changing this to a x minus 1, we've moved the center. Here, the center was at 0 because 0 makes the inside part equal 0. Here, the center is positive 1. So it's not at 0, it's actually at positive 1. And the reason is 1 makes the inside part equal 0. So here we're a distance of 2 from 1. So we can go up to 3, and we can go down to negative 1. So here the answer is everything between negative 1 and positive 3. And that means we're a distance of 2 from 1. One final thought in example 1 is this. Going back to this inequality, what happens if I also include this? So not just the absolute value of x is less than 2, but once it's strictly greater than 0, how would that change this answer? And what it does is it throws away one number. This will remove the center, which is 0. If you think about it, if you put 0 in place of this x with this here, it equals 0, and we want it to be greater than 0. So you can do something similar to this inequality too. Here, it removes one number from our solution, and that number is the middle. It's the center of the interval, which is 1. Again, if you put 1 in place of x, you get 0, and we want it to be greater than 0. So I'll note that if you have this, 0 less than the absolute value of x minus a is the center, but it's removed. Let's continue in example 2. Same idea. I'm going to state a few absolute value inequalities, and I want to graph them in the xy plane. Some will depend on x, others will depend on y, and depending on which it is, I want to restrict our answers to either the x or the y axis. So to start with, I want to graph, how about this? The absolute value of x minus 2 is less than 1, but also greater than 0. Since I put this x here, I want to draw our answer and restrict it to the x-axis. I have to know where the middle is, and that's at positive 2. Here, we're allowed to go a distance of 1 from 2, and including this part means we just throw away 2. So the answer looks like this. We won't include 1, we won't include 3, and we also won't include 2. But we're going to take everything in between those numbers. And on the x-axis, this inequality solves this. Okay, what about something like, how about the absolute value of y minus 3 is less than 1? Now here, the y means I want to go on the y-axis. So the middle is 3, positive 3 for y, which is here. And again, we go up 1 and down 1. We're not throwing away the middle part of the interval. So I get everything up to 4, down to 2, and the stuff in between. Maybe 2 others. What about the absolute value of x plus 3 is less than 1? Now this is weird. These are both negative. How does a positive change where the center is? This time it will be at -3 instead of +3. So it's the opposite of the sign you'd expect. So that's here. We go 1 to the right, 1 to the left, and this is our answer. Everything from -4 to -2, and the stuff in between. Okay, one more. How about y plus 2 is less than 2? The middle is at -2, so we're here. We're going to go down 2 and up 2. So this means our answer starts at 0, goes down to -4, and it's everything in between those numbers here. Okay, so now on to the precise definition of a limit. In example 3, I have a graph of f of x. Now, this function f is a piecewise function. Sometimes it's the function, this is linear, and it's x plus 1, y-intercept of 1 and slope 1, except for at 2, where I removed the point and I put it down here at 1. The way you can express this as a piecewise function is, well, it's x plus 1 as long as you don't use 2, but if you do use 2, I'm defining it to be 1. Now, we've done this before, but what is the limit as x approaches 2 of this function? To figure that out, it's tempting to say, oh, the answer is 1. But the idea of a limit is to actually not use this number, but get really close to it. So you have to actually use this part of the function. And as we get close to 2, the graph appears to get closer to 3. And in fact, that is the answer to this limit. Now, in doing this limit, we're using some imprecise language. For example, I say we approach 2, or we have to be close to 2, or near 2. And when we are, the y values are near 3. So let me just write that down. When talking about limits, we were saying things like, if x is near but not equal to 2, then y, or f of x, is near 3. And this is imprecise because, well, how close? Nothing in this definition really tells you that. Let's try to bring some precision to this statement. So example 3 says, we have this graph of f below. Suppose y minus 3 is less than 1. Can we find a delta greater than 0 such that the corresponding x's satisfy this inequality? There's a lot happening in that statement. I'll try to describe it on this graph. First, we're making this assumption. This has to be given information. You have to know how far you are from some given limit. So in this case, we're saying 1. If I mark that over here, the middle is 3, and we're allowed to go a distance up to 1 away. That's up to 4 and down to 2. The goal is to find some distance around this corresponding x value such that any x value you pick here will be mapped to a y value that's within 1 of the limit 3. A nice, easy visual way to find it is to do this. You take 4 over to the graph, bring it down to the corresponding x value, and do the same thing for 2. And it turns out that if you're within a distance of 1 from 2, so you don't go past this spot or that spot, all the x values in here will be mapped to y values that are within a distance of 1 from 3. The exception being at 2. Here, if you use 2, it takes you to 1, and that's beyond a distance of 1 from this limit. But that's okay, and that's the reason for this greater than 0 part. It's saying you're actually not allowed to use the number 2. And we said that with the limit itself when we first defined it. You approach 2, but you actually don't technically use the number itself. So what is delta? We just found it. Delta is equal to 1. So you'll be given this number here, and the goal is to find this number here. So you're told the distance you are from the limit, and then you're looking to find the allowed distance you are from this number. Just some notation here. This given number 1 here, we'll call that epsilon. In this case, epsilon is equal to 1. So you'll be given an epsilon, and the goal is to find a delta. Now, just a second look at this. It won't always be convenient to use a graph, but there's actually a nice analytic way to do this too. So I'd like to go over that. So your given information is that y minus 3 is less than 1. That's our starting point. And your goal is to find an x minus 2 that's less than some delta. Well, the y values, if you're not allowed to use 2, are always equal to x plus 1, so you can just replace this y with x plus 1. So these two statements are equivalent because y and x plus 1 are the same thing. Now, when you subtract and you do x plus 1 minus 3, you get x minus 2 is less than 1. And in just these 3 steps, we went from our assumption to something that looks exactly like the answer over here with delta. And delta is the number that's sitting right here. So here's a way to find delta not using a graph, by actually using some equations. Now, you do have to include this condition of greater than 0, but this still tells you that delta is equal to 1. Second point is the delta we found, this delta equals 1, is actually the largest. It's the largest delta. And the reason is you can always use some smaller distance. So here we said you can go a distance of 1 in this direction, a distance of 1 in this direction, and all the x values will be mapped to y values within here. If you use delta is equal to a half, so you went from here to here, it still is true that all those x values get mapped to y values in here. So when doing this process, we are finding a delta, but technically it's the largest such delta. Let's try this idea again, but with a different function. So this time, let's use f of x is equal to 2x plus 1. Suppose the absolute value of y minus 3 is less than 1. Can we find a delta such that the corresponding x's satisfy this inequality? One thing to mention first is this is really trying to address the idea of a limit. In fact, we're looking for the limit as x approaches, well, we want to approach the number 1, so that's the number here, so I'll put 1. The function we're using is 2x plus 1, so I can put 2x plus 1 here. And it should be equal to the middle of this interval here, which is 3. And it makes sense if you put a 1 here, you get 3. So we're really trying to ask the question of what is the limit as x approaches 1 of 2x plus 1? But here we're adding some precision. So first we're going to say, suppose you're within a distance of 1 from the limit, which is 3. So that means, again, you can go up to 4 or down to 2. But this time the line is steeper. It's 2x plus 1 instead of just x plus 1. If you want to find the distance around 1, you can draw a line going over to the function like this, drop it down to the x-axis, do the same thing here. And we're looking for, well, what's this x value and this x value? My drawing wasn't very good. It's not lining up perfectly on the graph. I think what I'm going to do is use an analytic method. I'm going to start with our assumption and say, well, I know y minus 3 is supposed to be less than 1. But here y is the function, which is 2x plus 1. And if you simplify 2x plus 1 minus 3, you get 2x minus 2. Now, I'm looking for an x minus 1, and I don't see one. However, I can factor a 2 out from both terms. And now I do see x minus 1. It's 2 times x minus 1. If we're dealing with an absolute value, we can take the absolute value of 2 and separately the absolute value of x minus 1. But the absolute value of 2 is just 2. I was hoping to see an x minus 1 and just a number on this side, but there's this 2 here. you're allowed to divide this to the other side, and we get a half. In fact, that's the delta that we're going to use. So for this question, delta equaling 1/2 is the largest delta for which this problem works. What does that mean? That means you can go a distance of a half from 1 this way and that way. So it's that this spot is supposed to be 1.5 or 1.5. And this spot here, well, that was supposed to be 1 minus a half or just 0.5. So that's how far you can go away from 1 in order to make sure that every x value in here gets mapped to something that's a distance of 1 from the limit. Now for this question, I did include this, greater than, because technically in a limit, you don't have to use the number 1. Here though, it really doesn't make a difference. The number 1 does in fact go to the number 3, so there's no issue with putting 1 in place of x. Essentially, this delta works if you have this 0 less than or not. One final thought for this problem is, so you have to have this given information. You have to say, well, there's some distance that we're choosing, and then we're finding a distance down here. And that distance was 1. And this was what we called epsilon. And then down here we found our delta. What if I changed it? What if I started with epsilon equal to a half? How will that change what the delta is equal to? If you think about it, if you put a half here, meaning you can go up to 3.5 and down to 3.5, the only thing that's changing in all this work that we just wrote is that this is a half, that's a half, that's a half, that's a half, and so on, until you divide 2 to the other side of the equation. So if there's a half here, and you divide by 2, you get a half divided by 2, and that's 1/4. So the observation to make is, whatever number you put here, you're going to divide it by 2 to get your delta down here. So if you have 1, you get a half. If you have a half, you get a 1/4. If you had epsilon was equal to 0.1, then half of that is delta, which is 0.05. In general, you can say, if you want a formula for delta, it's going to be epsilon over 2. So that's a formula that will work for any number that we put here. In example 5, we're given this limit, and the limit's equal to 2. The goal is to find the largest value of delta that corresponds to epsilon equaling 0.2 in the epsilon delta definition, which is the precise definition of the limit. Down here, I included a graph of x cubed minus 5x plus 4. And if you approach 2, the corresponding y value, the limit, is also 2. Now this question is saying, well, if your limit is 2 and epsilon is equal to 0.2, if you go up 0.2 and down 0.2, how close to 2 do you have to be down here so all of those x values get mapped to all of those corresponding y values? So that is, you can go up here, which is 2.2, you go up 0.2, or you can go down here to 1.8. And the corresponding x values are going to be, well, here 2.2 hits the graph here. It's going to be like really close, but it's going to be something down here very close to 2 and beyond it. Down here, we're going to get another x value that's going to be less than 2. For this problem, I think it makes a lot of sense to use a graphing calculator or something you can use to solve equations. Here's what that process will look like. In my graphing calculator, in place of y1, I'm going to enter the function x cubed minus 5x plus 4. And what I want to first figure out is, well, where does the horizontal line 2.2 intersect the graph, and can I find the corresponding x value for it? So I'll do this in a couple of steps. In place of y2, I'm going to enter in the equation 2.2. I have this graphed in my calculator. The next thing I'm going to do is hit the second button and then where it says calc. And it gives me a whole bunch of options, but if you choose the fifth option, it says intersect, which is what I'm looking for. I'm looking for when this equation intersects that one, and my calculator will actually tell me the x value. So I'm going to choose the fifth option. It asks first curve. And what you want to do is move the point until you get really close to the intersection point by pressing left or right. So I'm going to move this over to the right, and then you hit enter. It says second curve, you hit enter again. It asks for a guess, but you just hit enter again. And here, what I got for the x value, so for this one here, I got that x is equal to 2.027911. So that's pretty accurate. Now we want to do this process again, but this time we're going to swap out y2 from 2.2 to 1.8. So now this will graph in the xy plane, and I'll go second calc, choose intersect, and try to find this point here and its corresponding x value. Okay, so I have the graph. I hit second calc and chose intersect. I move the point over to the intersection point, and it says first curve, so you hit enter. Second curve, I hit enter. Guess, I hit enter again. And okay, for this one, it gives me an approximation of x is equal to 1.9706961. This will help us find our delta. Delta is either the distance from 2 to this spot or from 2 down to this spot. And I want to choose the smaller of those two distances. The reason is, if you choose the bigger distance, you might fall outside of an interval and get y values that are outside of this interval. So to figure out delta, what is delta equal to? I'm first going to I'll do this minus this. So that is 2.027911 minus 2. And then I'll do 2 minus this number. So that is, I'll also check 2 minus 1.9706961. And between those two, I'm going to choose the smaller of the two values. The two numbers I get are close, but one is 0.027911, and this one is 0.02293039. So the smaller of the two is this one. So this is smaller, and that'll be my delta. And I guess I'll round it to 4 decimal places. And if I do that, I get 0.0279, and it actually rounds it down, so it does make it even smaller, but that will be the delta that I can use to ensure that any x value I choose in here will be within 0.2 of the limit over here.